Hello. So I want to talk about coverage bitmasks for efficient rendering algorithms. You can see this image here. That's not made by me. This is from Professor Dr. Eisenman. He and others use bitmasks very efficiently in rendering algorithms, and I found a common theme among multiple papers that use them. And so I tried to collect that and present it here in a way so that other people can also learn from that and use that efficient tool to accelerate their rendering algorithms. So short overview. So some people don't call it coverage bitmasks. They call it visibility mask or occupancy or occlusion or blocker bitmask. There's multiple names for that, but they seem to be all very similar in a way. In general, it is a tool to process binary decisions in bulk, and that means more efficiently. So this is a short introduction, and there will be mentioning some applications. You will see the background of those slides will be more purple. And then I'm trying to deconstruct what those applications are doing and then have a bunch of references as well. And there's also bonus slides that has more applications and more information if you're interested. So I am Martin Mittring. I'm a principal software engineer at Seed, at Electronic Arts. More about Seed in a minute. And I worked on multiple game projects like Far Cry, Crysis, Gears of War 3, and other things. But I'm always working on the engine, mostly working on the engine side. So I'm having experience with CryEngine and Unreal Engine, and also the transition from 3 to 4, and worked on a lot of different things, and came across a lot of tools. And the tool that I want to talk about is the coverage bitmask that I'm using. So SEED is the search. SEED means Search for Extraordinary Experiences Division. And it's a small group within EA. This is Pika Pika. You might know this image if you have heard about us, or have you seen this presentation that was talking about our engine that we developed for research. It's an R&D team within Electronic Arts since around 2015. And I've just joined in January, so most of the history is from others. It's a team of 40 right now, and a lot of them are actually now on machine learning or have experience with machine learning. And they're all over the world, so Stockholm, Montreal, Los Angeles, Redwood Shores, London, Vancouver. We're doing applied research, cross-disciplinary, and have projects that range from 6 months to 5 years or more. We're collaborating with the games that we have within Electronic Arts, game teams, and also the central groups, like Frostbite, for example, but also external connections we have to the hardware vendors and software vendors, and influencing standards and having academia connections. We're also sharing, so we present and publish, so we have a lot of publications. You can find open source as well. So if you want to find more about Seed, there's the seed.ea.com or at Seed, you can find out more. So show of hands, please. Who knows about triangle rasterization? Who could write a rasterizer, a triangle rasterizer by themselves, or did already? Or, well, if you want to know more about it, I can tell you a bit more. It's kind of useful knowledge, so the following slides will be really hard to understand if you don't understand how the general triangle rasterization works, so I want to explain it at least briefly. So classic triangle rasterization, how it happens on the GPU, is the goal is to find all the pixels that are inside a triangle. You can classify the pixels based on the half space defined by the edges. You can see here there are the 3 edges. They are forming a half space. You're either on the left side or on the right side of that plane. Here it is in 2D. And you can classify those pixels, and the ones that are all inside, all on the left side of this edge or right side, those ones are inside the triangle. Well, it's not completely true it's not the full truth here, because if you're sitting directly on an edge, you need some kind of special handling to make sure that an edge, a pixel that sits on the edge is not counted twice, or is not counted, or is producing a hole. So there's some extra rules needed for that, but it's not that difficult. If you want to have anti-aliasing, then you can classify multiple pixels. So this leads to MSAA, and so you can have a bitmask. Again, there's already the first bitmask being used, and then you can classify those multiple samples within one pixel, and that's MSAA, multi-sampled anti-aliasing. And the fixed function hardware in the GPU has multiple stages. Depending on how the hardware looks like, it's a little bit different. But let's say you have a tiled renderer, then maybe your tile size is 1 megabyte. Then you have a large tile. You need to figure out which triangles fall into this tile. So you need to have a conservative decision which triangle is touching the tile. So it's a slightly different computation than finding which pixel is inside a triangle. This time it's a conservative decision. Also, a little bit lower resolution or smaller tiles might be another kind of, is like a coarse raster. Also, like here, it's, for example, 8 by 8 pixels. You want to make the decision, is for this 8 by 8 block any pixel of the triangle inside this block or not? And then you go one smaller for a 2 by 2 block, and then you can still make for every pixel the decision if that one is inside or not. Again, that's a mask. And then you have for MSAA, you have the mask if you're touching this one, as mentioned before. And depending on what MSAA level, 2 or 4 or 8 or something you're using, you have more or less bits for that. And the hardware is fast because it can process those pixels in parallel. And those decision-making things are actually executed with hardware that runs in parallel. But the software can do that too, because in software you usually have something like a machine word, like 64-bit or 32-bit. And so you can process bits in parallel very efficiently. And that's the whole trick around it. But there's a little bit more to it. So I want to explain those things. So how did I get there is because I was thinking for my work at Seed about real-time rendering of large detailed worlds. It's just one of the images that was produced by doing that research. And the problem is that you have many objects. So in order to process many objects efficiently, the CPU is just overloaded at some point. There's not enough performance on the CPU, but a GPU can handle it, because the GPU can process a lot of units in parallel, and it's just more suited for that task. So GPU-based rendering is probably what you want. But small geometry also means that if you're using the fixed function hardware of the GPU, the hardware rasterizer, then you're overloading that part, and there is limits of how fast the hardware can run this way. And so maybe we should avoid the hardware rasterizer. And also additionally, you don't want to have the geometry being too small, because anything will be wastefully computed if it is too small. So a good mesh level of detail algorithm attached to that one makes sense. And then you're having an even sized geometry, but you want to have kind of small geometry. So a rasterizer that is suited for that is maybe faster than the hardware rasterizer would be good. So you could make your own rasterizer, and that's what I tried to do. And in this case, you want to be efficient, so you want to only compute the areas that are needed to be computed. And in this case, a conservative bitmask actually solves this problem to figure out which pixels, which areas are covered by triangles. So first time I'm using the bitmask here in order to efficiently do a GPU rasterization algorithm in software. In software, in this case, means in the shader. But if I want to have anti-aliasing, then I need to have samples within a pixel. Like let's say I have 32 samples, that would be high quality anti-aliasing. For that, I can use a pre-computed edge bitmask. So again, another use of coverage mask. I will show you in a second how that works. And there's another use for a coverage mask, which is if you want to have translucency being efficiently rendered, one way of doing that is stochastically. You can make a decision, is that subsample being part of your opaque object or not? You can rasterize it based with some percentage, and that decision allows you to render with partially see-through materials, and you can do that per pixel, but that will be very noisy. If you do it per subpixel, like let's say you have 32 bits, then you can do it stochastically with a bitmask, and that is less noisy. So you might be asking, where's the connection to mobile? This sounds all like a very expensive thing that you can only do on desktop hardware and consoles. I mean, look at Nanite. It can do software rasterization, and they claim up to 3 times faster, which is great. I mean, if everyone, why would you not want to have it faster, right? So I believe that on mobile there is a draw call performance problem, and this is what Nanite is solving. And there's also you kind of bitmasks are solving the problem of efficiently. Well, they're solving can solve multiple kind of problems, and it's in general because they're in bulk doing multiple things that formerly had to be done with individual math operations. And so by doing it in bulk, you can be more efficient, and that's always important for mobile. Maybe you're actually using already alpha-2 coverage, for example, or some level of detail cross-transition. For example, on the bottom right, you can see how on NVIDIA alpha-2 coverage looks like, or on Metal. They have to have, it seems like it's not defined completely, so they have different implementation. But in general, it's a tool that creates from an alpha value between 0 and 1 a mask that says these pixels are see-through or not see-through. And this way you can, with 4 times MSAA, for example, or here I think it's 8 times MSAA, you can get 7 shades or 8 shades, depending on how you count. And if you add a dither pattern on top of it, you get more shades. So this is why they look different, those images. So that's alpha-2 coverage. That's already a very good application of those bitmasks together with MSAA. So I believe everything comes eventually to mobile. Fast GPU integer math is probably needed for this one. Maybe more GPU-driven rendering features, maybe atomics. There's a lot of things that haven't reached maybe some mobile yet, but I think it can come. Why not? In fact, a lot of stuff has reached mobile even faster. Like there's more ML hardware being in mobile than on desktops, I believe. And the machine learning hardware could help you to accelerate your other algorithms. You might get it for free because there's dedicated hardware available, and if it's not used, it's a waste. And it can very efficiently denoise something. So if you're rendering with a stochastic output with some noise, then you can denoise it with some ML algorithm. And so maybe by producing data that is noisy, you can be accelerating your rendering algorithms. And I also want to say that a lot of mobile hardware is rendering through immediate mode tiled render. So it's like in tiles, and it buckets the whole render screen into multiple parts, into multiple buckets. It splits the screen into tiles, let's say one megabyte tile or something, and then it renders only those tiles one after another. And that is very suitable for low triangle density because you have to go through your geometry multiple times. And if you have a high triangle density and over time you want to have the expectations go up, you might have problems with that, doing it the old way. A funny thing is that ray tracing already has a scene representation on the GPU. So I believe running the tiled-based algorithm with ray tracing and then traversing the GPU, traversing all the draw calls on the GPU side makes a lot of sense, and could be also happening on mobile sooner than you would think. And then something like Nanite can happen on mobile. It might not look the same way, but I think the implementation might look different, but the general idea might be the same. So this is one of the applications. So this work is a CPU algorithm. The goal is to compute a tight potential visibility set, meaning which draw calls are visible from that camera location, and you compute that on the CPU. The CPU has SIMD, or in this case is AVX2, and you can process a lot of bits in parallel with AVX2. In this case, it's 256 bits, and because the machine word there is 32-bit, and it's 8 of those ones, you can process a 32 by 8 tile. You can see on the left bottom how such a tile looks like. It's not it's a rectangle, not a square. But on the right, you can see how this rasterization works. You can, in order to figure out the bitmask for a triangle, like where is the triangle and where is not the triangle, the final bitmask here, you can compute it by ANDing the multiple bitmasks from the multiple edges. So you have one edge, another edge, another edge. You combine those bitmasks with an AND operation, which is very efficient, and then you create the triangle bitmask. In this case, it's all done with math. So it's a regular grid, and math is more suitable for regular grid. the technique is rasterizing the occluders, and it's testing occludees against those occluders. So this is a triangle rasterization on the CPU side. And it's a good idea to do that under certain conditions. The CPU allows you to cull draw calls. That means you're culling work very early because that's where the work starts. So you can cull even the setup cost of draw calls and all that stuff. That's good, but it's kind of not the most efficient way if you're doing GPU-driven rendering anyway. And the draw call granularity is kind of large, so you could cull at a smaller granularity as well. This work, different, is this different and the same. It tries to be as fast as possible to render in software on a GPU. So it avoids the fixed function hardware unit and tries to do in CUDA, making a really performant GPU rasterizer. And the benefit, I mean, there is already a rasterizer on the GPU, but the benefit here is, first of all, just as an exercise to see how fast it goes. So you can see the comparison is like hardware is still faster, at least at that time. But it also has benefits because you can make more sophisticated algorithms about frame buffer blending and all that stuff. So you can prototype things that maybe the hardware cannot do yet. In this case, it uses an 8x8 coverage mask, and that mask is actually a very small amount of bits, but for best cache performance, it actually uses some mirroring tricks and all that, so to get really the best performance out of it. But still, in this case, it's not fast enough. So when this came out, everyone was very interested in it, but it's not, when you see that it's still slower, you really don't want to hop on it. So it takes quite some effort to get it fast. So even that one was already very good, but over time, the shader units in GPUs get faster and faster because that's where a lot of the work is. But the fixed function hardware unit to rasterize wasn't getting as much faster. So it's kind of, over time, this becomes a different topic as well, where basically more and more flexible programmability is favored inside the GPU. So how can you implement the bitmask yourself? I showed, you've seen before that you can compute the bitmask for the different edges and then combine them. And you can do that with math, but you can do that also with a pre-computed edge bitmask. So the pre-computed image that is used here, this is the visibility sampling GPU and applications. You can read about it more in this presentation, or I think it's even older, that it's referencing some older paper, efficient coverage mask generation for anti-aliasing. So generally, you first, in order to solve the triangle, you need to solve the edge. So let's focus on the edge only. So if you have one edge and you want to know for one edge, I'm on the left side of the half space or on the right side of that half space. You can compute it, but it will be a lot of computations. But you can pre-compute it if you have some kind of key that allows you to look up the right value based on that key. So in this case, the key is two values. It's an angle and a radius. So the angle and the radius means 2D, so you can store everything either in a 2D texture or 2D array, and that visually will look like this if you take a hue transformation. So that means your edge has an angle and it has a radius, like a distance to the 0 point, and this way you get this kind of image. And if you make a lookup into that one, you can make a lookup and query the bitmask, let's say 32 bits, and those 32 bits give you the information about is that point on the left side or on the right side. There's a minor error, but that's generally okay. If you have that for one edge, you can combine it up with the other two edges, and then you're getting combine it up with an AND, binary AND operation, then you get the information for a triangle. And that means 3 memory lookups to get that one, and two AND operations. So you can do that efficiently with a 16 by 16 texture lookup, and you're outputting a 32-bit mask. So it works pretty, quality-wise, pretty good. And you can express any convex shape this way, but obviously most efficient is a triangle with 3 edges. I want to show you how that looks like. So this is an implementation of 2D triangle rasterization, and you see there's some kind of overlap here. At that time I wasn't handling the occlusion or Z buffer or the triangles were not hiding each other. But if you do it in 2D, it's actually simpler, and that's why I started with 2D. Now you saw that everything blurred. That's actually a trivial little thing in this algorithm, because you can scale the bitmask when you query it, and by scaling it you can make it larger, so you get something like a Gaussian blur out of that. And if what I'm varying here as well, you see the quality is going up and down a little bit. The quality here is because I'm using a lower resolution bitmask, and so that it has more facets, and by changing that you can trade quality for performance. And this is another example, another test application that I wrote, where it visualizes the two kind of pre-computed bitmasks that I have. Two of them. The top line shows you the one for conservative rasterization, and the bottom one shows you that one for anti-aliasing. So for conservative rasterization, you want to know which bits would be for sure outside on the right side of your edge of your half space. And so you can see how these bits, this is an ordered grid here, it gives you the information about is that bit for sure inside or not. So it's kind of conservative. You can see that there's different colors in different locations of that bitmap, and this is where the lookup happens, is this sort of white point here moving. And this is just some reconstructions that show that everything, kind of a zoom-in version as well, that shows everything was happening correctly. And if it wouldn't be, then it would show up some red colors here. Now here you can see how the same happens on this sample distribution that is more uneven. It's actually optimized for different angles to be all very even and producing as many shades as possible from different directions. So this sample distribution is used for anti-aliasing, and you can make circles or lines with anti-aliasing. But again, I can scale the size here, and when I'm scaling the size, you can see that the point set gets larger than a pixel, and it gets blurrier for the circles, or blurrier for the lines. Or if it's very small, then there's no anti-aliasing anymore. Okay. And I have some learnings while implementing that one. For example, some trivial one is like 32-bit per pixel is pretty good high quality anti-aliasing. That gives you like 32 shades, and that's good. But if that is costly, is too costly, like there's a lower quality version that can be done. Like you can use the same 32-bit for a 2x2 quad, and then you have 8 shades per pixel. Or you can make some other trade-offs as well. But this basically allows you to reuse the same algorithm, the same table, maybe even for lower quality rendering. So it's a good trick. What's needed for watertight rasterization, to not have holes and double rendering, you can easily flip an edge if it's pointing downward. So consistently the edges should always be pointing downward. So you flip them and invert the mask if that's not the case. So then you're avoiding this problem. The Occus tangents to kind of compute the angle would be expensive, and I found an approximation that is rather trivial, and you can use it or you find something better. For me, it solved my performance problem, so that's what I used. Another work is that's rather straightforward to use it for font rendering, because font rendering doesn't have any Z occlusion problems, and you want to have anti-aliased fonts anyway. So this blog post is telling you how to do that, and the goal is to do font rendering with anti-aliasing. But it's also a little twist. It's not only rendering the fonts, it's also when I have a cache of those font characters, the glyphs, and that cache is maintaining that bitmask. So there's a 4x4 bitmask for each pixel to give you 16 shades, and it's a rotated grid for to make near vertical or near horizontal edges look better. And it's especially for font rendering a good idea, because that happens very often there. And the bitmask is stored, as I mentioned, for each of those glyphs, and that allows you, when you blit the pixels, to actually blit them with subpixel precision. So you can position your characters, especially for small fonts, that's important, you can position them at a subpixel precision. So in this case, it's not only computing it, it's also storing it for efficient anti-aliased blitting of characters or glyphs. In this case, it's using a 32 entry 1D table, 2 of them, instead it could have also used a 124 entry 2D table. So it basically saves memory and maybe cache performance, but it also is a rather simple implementation if you do 2 1D lookups instead of 1 2D lookup. This one is interesting because of the goal that it tries to solve. It's for area light shadows. It's a hard problem, and it solves it rather elegantly. It's like in parallel you can make, let's say, 128 rays shooting towards your light source. You have to imagine each of the rays that you're shooting to your light source is just the information, is it occluded or not, as a bit, and then you have 128 bits, and with those ones you can decide, depending on how many bits are on or off, how much you're in shadow or not. So each of those bits is representing if a ray is occluded towards the light in that cone. And it works like that, similar to those half spaces, but in this case, this half space is defined in 3D. So that makes it more complicated. It's not a 2D half space. You have to parameterize your table lookup now with 2 angles and a distance, and also it needs to be a bit higher precision. So this is a rather large texture. It was 128 times 128 times 128, and also because the area can get really large, 32-bit is not enough, so it uses 128 bits to have less noise. And then additionally, there's also jitter on top of it to kind of randomize that further to make the cache trashing even worse. And then you're getting some kind of noise, but you're getting not this banding artifact. So I think it's interesting, but it has, with that implementation, it's quite costly. But I think maybe GPU hardware could go there easily because of it's kind of like a optimized ray tracing version. Maybe use the same data structures. This work here is like if you want to do immediate mode rendering, like you're submitting all your triangles, they get executed one after another. You don't want to process your geometry twice, and you want to have anti-aliasing, then you could do only MSAA, and MSAA is expensive. You have to if you want to do MSAA with gbuffer, it's even more expensive. Now this one is doing kind of a twist to it. It stores, instead of n MSAA samples, like 8 for example, it uses only 4. And it's a little bit of savings, but it figures, it gives each of those 4 samples a weight, and the weight comes from the coverage mask. So coverage mask is used to decide on, for those 4 gbuffer samples, what is the weight for that sample. It's kind of a higher quality solution, so it will produce way higher quality than 8 times MSAA, as you can see here, but it also comes at a cost. In this case, it's an audit grid, it's 64-bit, and you have the usual 3 edge lookups, and then your binary AND. And as I said, it stores 4 gbuffers per pixel. It additionally stores the mask and also a triangle plane equation to get z-buffer intersections correctly resolved. Maybe with hardware support, this could be a really good solution. This one is interesting. It's a approximate ray tracing solution, and at the end of this pipeline, it computes multiple things, and then in the end of that pipeline, it has a 1D bitmask. Think of a 32-bit bitmask. And that 32-bit bitmask is basically the geometry coverage along a ray. So if you want to know if you have a hit intersection with this bitmask, you're just testing the bit. If it is on, then you know this is a hit intersection, and you can also find the first intersection by just finding the first bit either from the left side or the right side. And well, you have to prepare your data so that you can, with a single lookup, get this information for an array. So the steps per frame that are being done is first you're rasterizing your geometry to the base occupancy map bitmask. And that's kind of a volumetric grid of bits that stores if there is occlusion or not. if there's an occupancy or not. And that one is not aligned yet to the rays, but you have this one base occupancy map that you produced, and then in the second step, all happens per frame, it rotates this base occupancy map towards different directions. A limited number of ray-aligned occupancy maps are getting produced by just rotating the base occupancy map. And that is independent of the scene complexity. The first one, the voxelization, was dependent on the scene complexity. But this one is not. It just makes a few decisions about how the rays are like a few pre-rotated versions of the base occupancy map. And then when you want to do the ray tracing, you make you figure out which of the diverts that you have stored in the ray-aligned occupancy map is the one that is closest to your ray. And then you make a lookup, and then you get an approximate version of ray tracing you approximate the ray that you're having as your input ray through this method. Now, this is really approximate, if you can imagine. So one level to improve this further is it jitters this information every frame. So it jumps around like crazy and produces more resolution this way. It jumps around during the voxelization, but it also jumps to a different occupancy map angles. And once it's done with that, then it's still kind of a noisy result. So denoising that one as a following post-process is necessary. And the paper mentions it could be also used with cascades. Or if you just do it per object, I think you can also do larger scenes. So very approximate. But in many cases, ray tracing is almost too precise. So maybe this is an interesting idea. So summarizing a lot of things, a lot of those papers before, I noticed there's a usage axis. One is like the position, a spatial axis. You have multiple dimensions depending on application. You can have, for example, a 1D domain, like a line light. You can have a 2D domain, that was the anti-aliasing, or 2D could also be depth of field. When you look at the bokeh shape, it's a 2D shape. So you can distort your image. You can see on the right here how depth of field could be stochastically solved as well. Or for 4D, for example, it's like portal-to-portal visibility. It's like a 2D portal visible to another 2D portal. You can store that in a 4-dimensional table. And it's also depending on what primitive you're caring about that you want to rasterize into the bitmask. Let's say a line or a triangle or a quad or a disk. You can construct it from edges or half spaces in more general. And that is a common theme. But it's also possible to solve motion blur. On the bottom right, you can see stochastic rendering with motion blur. There will be a temporal axis. And there's another axis, which is the probability. So you can make a random decision if something is see-through or not see-through. And that is the usual alpha to coverage. But you can also make it more sophisticated and add some things to it that you want. For example, some people add the triangle ID or the object ID to the alpha to coverage so that multiple alpha to coverage rasterized objects are not occluding each other in the wrong way. And you can also raycast volumes as before seen in that presentation. Okay, and then there's more. So if you look at the value that is being stored, you can store a value that is giving you a conservative decision, like the bitmask can give you a conservative answer. I think there's the Bloom filter as well that could be mentioned there as an interesting technique. And stochastically, it can give you a decision, so it's approximate in that case, or it could be an exact decision. Are you inside the triangle for sure? You can use more or less bits, and that gives you a different quality and performance trade-offs. You can use the bit order in some ways. For example, in the Ray 32-bit case that I mentioned before, the order is really a spatial order, so that was important in order to find the first hit. The location of the samples can be like ordered. It could be a rotated grid, a stratified grid, blue noise grid, or just in generally some kind of density distributed one. As I showed before, did I show that? Let me think. No. I need to check. Sorry. Yeah, also you can vary every pixel, every lookup that you do into this mask per instance, kind of randomly rotate it or something to produce more high quality results. Because of that pre-computed bitmask has limited resolution, and if you use multiple different results and rotate those ones, you can get better quality, if that's possible. And there is a general math versus memory trade-off. So should you use a pre-computed bitmask or should you compute those bits? I think hardware has an advantage in this case because it can always easier compute something in parallel. There's another method that is not using half spaces and an AND operation, but it's actually counting the number of intersections with the surface or with the edges. In font rendering, it's rather easy to explain. You can see that a line, when you want to have a point in polygon test. So you take that point and you take a line from there to the outside. And you count how many times you're hitting an edge or a triangle. And if that's an odd number or even number, you know inside the object or outside the object. And if you do that with a 1D, if you do that with, if you count those ones, that gives you the result. But if you want to do that in parallel for a bitmask with multiple, then this is more the appropriate picture. You can do that. For example, you want to know, I am behind that edge on the right side here or not. So you can compute that. You just do it line by line, and you make the decision of I have a few bits, and then you're shifting them depending on where this line, where this edge is. And so you're shifting bits around. So this is rather efficient if you have a line. That's why there was a 32 by 8 bit mask in the beginning with the SIMD, because that was efficiently done with bit shifting. But if you have an irregular sample distribution, then it's probably better to do a pre-computed mask. And in this case, you can still decide on in which order your samples are stored. And if you want to have this fill from boundary method, you can actually, once you sort them by Y, for example, then you can mask out the bits that are below it and the bits that are above it. And then you're getting the answer for, give me all the bits that are on the right side of this edge. So it's actually, you're taking into account where the edge starts and ends. This is different from the other pre-computed bitmask that had an infinitely large edge. It's a half space. In this case, it wants to know if my line, here this line is going to the left here, but here it's going to the right, is my bit on the right side of this edge. How many times I need to, if I'm counting how often, how much I'm hitting when I go left, you see those guys are all inside that edge. So it's possible to compute with a bitmask, even with a pre-computed bitmask. I guess I can explain that better. There is a inside test in 1D, for example, stencil shadows. Carmack's reverse, you can Google that, is talking about that. And for 2D rasterization, font rendering was mentioned before, so this is also possible to do it with this method. And it's more efficient and better than the edge method that I mentioned before, because that requires convex shapes, and fonts are generally not made out of convex shapes. And if you want to do solid voxelization, like you have a triangle mesh and you want to voxelize it, then you can also use that. And if you have a closed mesh, if it's watertight, you can do that with the hardware rasterizer and some XOR frame buffer blend. You can produce up to 128 bits in one direction, and the other two directions is just however large your frame buffer is. So this is a very efficient way of voxelizing geometry through the hardware and using bitmasks. If you do a single pass method, that's what I mentioned before, was this having multiple shifted bitmasks, but you can also do a two-pass method. So the Amiga Blitter was doing that. So you look here, there is a triangle being rasterized, and it was rasterized by first rendering lines to this bit mask here. It's a very large bit map in this case. And you see those lines have holes here, and this is because the line algorithm was differently than the usual Brazenham. It was only producing one pixel per line. and you see here is 1 pixel per line. And the reason is because that bit mask that was produced here, or that bitmap that was produced here, was later on processed by the blitter. That was just going from left to right. Every time it found a 1 bit, it flipped and started writing once, and then when it's got another 1 bit, it flipped and start writing zeros again. So it produces this filled polygon just from rasterizing those edges very efficiently. And you can output bits if you do, as mentioned before, if you just XOR those operations. So if you have 2 edges and you want to combine them, you just XOR the result of one edge into the other edge. But you can also compute it differently, and this is not using bitmasks actually, if you're doing it for the area. So if you imagine you're counting the number of bits, you can actually, by adding for front-facing objects and by subtracting for back-facing or back-facing edges, you can compute the area, and that gives you some analytical anti-aliasing. That's even higher quality, still a box filter, so there's limited quality because of that, but it gives better quality and it avoids the bitmask, because in the end, if you just want to have the alpha value, then that is the right solution. You don't have to do it. So some font rendering algorithms use that. The only problem is that is if you want to combine it up with other geometry. For example, you have 2 characters on top of each other. Every time you do just alpha blending, there's a limited, the result is not exactly the same that you would get from doing it with super sampling. So the reference implementation would give you a higher quality result than doing this. But it's a pretty suitable method for font rendering probably. So that's all. There's a lot of references. Please check it out. There's more, and there's more bonus slides as well. There's even more that fits to the topic. And I want to thank everyone that I was referencing, and all the people that work at Seed and work with me together on making this happen. It's a blast working there. And if you're interested in that, please reach out to us. We might want to have you joining. If you're checking out the bonus slides, I'm rushing through them real quick. Some anti-aliasing explanation for the ones that care about it. In the end, temporal anti-aliasing seems to be the best solution right now, but there is still artifacts, and it takes a while until images are converging. I guess machine learning was put on top of it and produces even better results, but there's limits to that. So producing some less noisy result could actually improve quality on the first frame right away. So certain artifacts would disappear, and that's also why I'm doing this work. Also, ML kind of machine learning, there's multiple algorithms that are now relying on this input that temporal AA also has, and then it can do anti-aliasing, upscaling, or frame generation from that input. So it's probably a good idea to produce a similar kind of input, even though it doesn't have to be done the same way. We don't have to do it through normal triangle rasterization. Maybe there's a different method. As long as it produces the same output, you could use the same post-processing methods. There's some relevant hardware features. Don't want to go through this one, but maybe you find it interesting. And here is if you're processing, if you want to write a rasterizer that rasterizes a triangle to compute efficiently which areas on the screen you have to consider, you can use this method. I want to not talk about it now. This is very interesting pre-computation work where pre-computation of a bitmask is used to later on decide how to correctly render with some kind of anti-aliasing, how voxels are occluding each other in a very correct way. And the coverage mask is used in a pre-computation here. This one is screen space ambient occlusion method that has some quality benefits over another method that doesn't do that correctly. There's multiple methods of improving the quality, and that's one way of doing it, but it seems to be very useful to improve the quality. And this work here, is also using the same trick, seems like, for global illumination. So the visibility problem that needs to be solved for global illumination is very similar to the visibility problem for screen space ambient occlusion. And here if you check out this presentation, you will see that in the end it uses a 128-bit mask to occlude the emissive surfaces or the bounds of global illumination. And there's another video that I don't want to talk about it right now. That's all. Thank you so much.